we've got a few problems to tackle. I'm not sure if it will be tackled. We would be able to tackle all the problems. We will start from problem 1, the computation, and we'll try to see how the computation should work. You did give a solution for problem 4, I guess. So we'll see that. I don't have an idea about that. And problem 6, part A, doesn't look like, I don't know. I'm not, again. I'm yet to understand the terminology of Bourbaki. Part B seems like something we can do.
I'm happy to look at whatever.
Problem 2. Problem 2 was from Rothman. That's also an interesting problem.
Felt like I made some progress, but I ended up with a question that I didn't know the answer to. So when we get to that one,
okay,
you can tell me whether what I'm thinking is something obvious or not.
Sure. Yeah. By the way, I was going through this paper. Okay, I think I closed. Now it is here. So this paper is about computing isomorphism classes of P groups, and they're using some kind of computer to do this. But they're trying to find equivalence classes for some values of P. And then for any P, they have kind of this formula or something. And they're using matrices. I don't know what they're doing with matrices.
I was curious. I wouldn't have guessed that P groups were that interesting. I would have thought that they would be pretty simple. I guess I haven't thought about it enough. I mean, oh no, I guess not. P groups aren't necessarily abelian.
No,
so I guess they could be complicated.
Yeah.
Yeah.
Rothman made us feel like they're
squared
abelian, but they aren't. Yeah.
Yeah. I think that p squared is always abelian.
Yeah,
p cubed, I think that there's always non-abelian examples. In fact, I think that Dummett does a construction for p cubed.
Does he? I think Dummett gave a solution to one of problem 1s. From the last one, I guess, P30. Yeah.
Yeah, I think that Herstein breaks it down in an exercise, but I think you're right about 30.
The number of non-abelian
page
groups
182.
Of order 3 to the 6 is 481. And the number of order e to the 6 is given by the following expression. Wow. So you have a formula that gives you the number of... Wow.
When was this published? Third date? 69.
Yeah. P to the 6. Do we have anything of P to the 6? No. Okay. So we'll see. Let's get to problem 1. The P set. Look at the P set. Right, so the first problem, you have to classify stuff. So how do you classify stuff? R10 explains this quite nicely. So essentially, we have to use the Sylow theorems to do something about it. So I think you give the proof for the first one, doesn't it?
Yeah, I don't think it's a very elegant one, but
You got
there's
it.
a general result.
Mm-hmm.
There's a general result that if the order is the product of two primes, say P is less than Q,
Mm-hmm.
and if P does not divide Q minus 1,
Right. It was
then
indefinite, I
your group
guess.
is cyclic.
Right.
I think that's everywhere. I think that's a common result that everybody
Right.
does or puts as an exercise. The reason is that
Mm-hmm.
the P Sylow subgroup and the Q Sylow subgroup are both normal in that situation. They have
Yeah.
trivial intersection, and I guess just using a counting argument, product of them has order PQ, so that it gives that it's the product of ZP and ZQ. I think that n equals 33 is a special case of that.
Mm-hmm.
But if instead of just waving our hands at that, we want to just think about it,
Mm-hmm.
I think that would be healthy. Because everybody also has results for, well, what happens if P does divide Q minus 1? What about groups of order P squared times Q? And you even gave us a problem similar to that, or that was working with P times Q or P squared times Q. Seems to be a strategy for putting these in boxes and analyzing them.
Right.
So what text are you in right now?
This is Rodman.
Ah.
Yeah, like before he gets into unitriangular matrices, which we're not going to see ever again. I don't think he mentions this one, or maybe, wait.
I don't know, concrete examples are not his thing.
Right. If there are Rj Sylow Pj subgroups, then Rj is a divisor of this, and Pj divides Rj minus 1. I don't know, is this too general of what we were speaking?
No. That's one of the big tools that we use. I think that's Sylow 3 or something.
Oh, yeah. The order of these Sylow theorems in different books is like messed up.
Yeah, agreed. So one of the big things that we use the Sylow theorems for is, first of all, show the existence of subgroups.
Right.
Then using this counting one, you can show that Sylow subgroups are normal under certain circumstances by looking at the orders of all the different subgroups. Once you have a normal subgroup, then you can start doing quotients and stuff.
Mm-hmm. Okay, so if we have to do, you did 33, so let's just go through that. Okay, 33 is, yeah, you just said, okay, if you have p less than q, then, and p does not, p divides q minus 1, does not divide q minus 1, then, it's isomorphic to, it's a cyclic group, right? Mm-hmm.
So I talked through the ideas.
Right.
So we know that there's a Sylow subgroup of order 3.
Mm-hmm.
And the number of those has got to divide 11 and be congruent to 1 mod 3. That was that theorem that you were just pointing at.
Right.
So the only divisors of 11 are 1 and 11 is not congruent to 1 mod 3. So that means that there's only one pre-Sylow subgroup, which means that it's normal.
Yeah.
And then going the other way around, there's a Sylow 11 subgroup. The number of such things divides 3. It's got to be congruent to 1 mod 11. Well, the only divisors of 3 are 1 and 3. 3 is not congruent to 1 mod 11. That means there's only one 11 Sylow subgroup. So
Mm-hmm.
both of the Sylow subgroups are normal, which means that HK equals KH. And we also know by looking at the orders of the elements in them that their intersection is only the identity element.
Right. Right. So,
So
yeah.
the subgroup HK is a subgroup of G which has order 33, so it's got to be the whole thing.
Mm-hmm. Mm-hmm.
And I think the same argument works for whenever it's P times Q and P does not divide Q minus 1.
Yeah. Right.
Sadly, none of the others are that easy.
Second one is
So
18. That is PQ squared.
yes, and so is 20. I guess
Yeah.
that one's P squared Q. So I guess the difference between the 18 and the 20 might be whether it's the larger prime that's squared or the smaller one, which is
Mm-hmm.
squared. So one thing, we're equipped to do, based on just the Sylow theorems, is to write down how many Sylow subgroups there are of each order, possibly.
Right.
You can write down all the possibilities. And then we need to start figuring out how to put them to get back together again.
Mm-hmm.
So I understand classification to mean have a complete list of groups of that order so that if you have any group of order 18, say, and it's going to be isomorphic to one of the groups on your list.
Right. So it's like the equivalence class of that order.
Bingo. And I think that the way that folks do this is if they don't recognize one of the groups, they
Mm-hmm.
write it down using a group presentation, like you did back in homotopy theory, I guess. Give a list of the generators and
Yeah,
relations
yeah,
between the
yeah,
generators.
yeah, yeah, yeah.
So I think that that's what's going to happen here. If I say that there are two Sylow subgroups, both of them are cyclic. Let A be the generator of one, let B be the generator of the other. Then there are going to be two groups of that order. In one of them, A and B commute, and in the other one, A times B is equal to B squared times A. For example,
Okay.
that
Yeah.
definitely has the flavor of what you did back in homotopy theory, right?
Right. So if we go back to homotopy theory, I think that there's this like nice table on Hatcher where he has like generators of the wedge of two circles, you know? Um,
Mm.
da-da-da. right here. So the covering spaces of the wedge of two circles is like this, and you have the generators and the relation between the generators.
So what do those symbols mean? Are those the things that are equal to 1? A squared equals 1, B squared
No,
equals 1?
this is just like this is a free group generated by these things.
Oh, it's generated by A squared, B squared, and
Right,
AB?
right.
Okay.
So these things
So
cover.
you put relations in there.
Right, sorry?
Somehow specify relations also?
Yeah, like
The homotopy groups aren't generally abelian, are they?
no, homotopy groups are not abelian. They can be abelian, but they're not always abelian. If they were, things would be nicer. Yeah.
Yeah. So generally you have to give not only the generators, but you also have to give relations between the generators or among the generators.
Right. So here he says this, I guess. The covering space of this wedge circle has a rich family illustrating most of the general theory very concretely. We view this as a graph with one vertex and two edges. Right, so he's like considering this as like a graph having two loops. So yeah, this loop and this loop. And the relation, there is a relation, because at some point what you have to do is you have to take the mod with respect to this free group, and you'll be using that relation to do something like that. Yeah, I'm going to be coming to that soon.
Okay, let's see. I'm flipping to page 105 of Massey's algebraic topology. So that's where he goes. He's been talking about free groups, and now he's going to talk about presentations of groups by generators and relations.
Okay.
Fortunately, he has a bunch of different books, different versions of the same books. The one I'm looking at is called Algebraic Topology and Introduction.
I'm trying to look something from John Lee. He has this book on topological manifolds.
One of the problems with describing groups using generators and relations is that it can be really, really hard to decide whether two presentations represent the same group.
Here's the thing, right? You have the
there you go, generators and relations. So that's, I think that even with what we're doing, some of that problem is going to come up, because we might be able to describe or to give a full list of groups using these semi-direct products. What's not clear to me is how to know whether you have any duplicates on your list. Whether you've just described the same group a couple different ways.
Right, essentially how to know which are distinct and thus the rest would be isomorphic.
Yeah.
But yeah, so Z mod n has this representation, presentation generated by this alpha, and the relation is alpha to the n is equal to 1 of order n, yeah. Okay. Right, because the thing is, in algebraic topology, you also have to do that. You need to find isomorphisms a lot.
So if I remember, one of the tricks over there is to abelianize it, and
Right.
and just see how many generators are left. I don't remember whether that's easy to do from the presentation or not, but
Right. So
because the number of generators doesn't really tell you everything.
Right.
It doesn't say that that's like a minimal set of generators. I think that's got us in the mindset of what we're going to be looking at.
Yeah.
Want to pick that example of 18 or 12, whichever one was you found worked out? Or Dummett does 12 and 30.
12? Yeah, okay.
12 and 30.
Artin does 12 and 12. Okay, only 12.
Yeah, Artin has a whole section on 12, huh?
Yeah.
Well, that section is 2 pages. Oh, and look at that. Oh.
Yeah.
Number 5. Instead of saying it's a familiar group, he says it's the group generated by X and Y with these 3 relations.
Ah. Yeah.
So you want to start there? That looks good.
That looks good, yeah. Order 12 has the alternating group and the dihedral group.
So if we had to list them, we would probably have come up with 1 through 4 to include on the list just by listing any groups we know of order 12. But let's see how you can start off. Land on one of those.
Right, so the 12 is p squared q 2 squared times 3. I believe that's also similar to one of the things we have 20, right?
Either the 18 or the 20 might be similar to this.
Yeah. Here I'm assuming p is less than q, so yeah.
Yeah, p less than q would be 20. And both with 12 and with 20, we have p dividing q minus 1. Okay, so starting from scratch, if we've got a group of order 12, we have a 2 Sylow subgroup, and we've got a 3 Sylow subgroup.
Right.
At least one of each. I'd use his notation. H is a 2 Sylow subgroup, a Sylow 2 subgroup.
Yeah.
I also wish that the books would be consistent with that, whether they call it a 2 Sylow subgroup or a Sylow 2 subgroup. I think I prefer Sylow 2 subgroup.
Okay.
In the 2 with group. Okay, so H is the Sylow 2 subgroup. That's got order 2 squared.
Yep.
And K's 3 subgroup. That's got order 3. The number of 2 Sylow subgroups has got to divide 3, and it's got to be congruent to 1 mod 2.
Mm-hmm.
So that could be 1 or 3. So there
Right.
might be one Sylow 2 subgroup, or there might be 3 of them. The number of 3 subgroups has got to divide 4, and it's got to be congruent to 1 mod 3.
Right.
So that could be 1 or 4.
Wonderful.
So there are either 1 or 3 2 subgroups. And there are either 1 or 4 3 subgroups. So we can't jump to any conclusions about H or K being normal right off.
Mm-hmm.
But one thing we can say is that the 3 subgroup K is going to be isomorphic to Z3, and the 2 subgroup is going to be isomorphic either to Z4 or to Z2 cross Z2.
Right.
Because since its order is the square of a prime, we know it's abelian.
Mm-hmm.
And then by the classification theorem, there are only 2 abelian groups of order 4.
Remind me, what
And
was
that's
that?
about all I'm confident saying.
Order 4, it was
Z4
Wait,
or
right.
Z2 cross Z2.
Ah, okay, yeah. And they're both isomorphic?
No, they're not.
No, they're not. Okay.
I know that H is isomorphic to one of those 2,
Mm-hmm.
and I know what K is isomorphic to. It's a really boring thing to say, but we do know all of the abelian groups of order 12. It's either Z4 cross Z3 or Z2 cross Z2 cross Z3. Duh. Because if it's abelian, then H and K are both normal, and we can just multiply them together.
Mm-hmm.
Just finding these non-abelian ones.
The non-abelian ones.
Oh, wait. Look,
Yeah.
I was wrong. How could I be wrong? Oh no, the Klein 4 group is just Z2 cross Z2.
Yeah.
I'm looking at his paragraph where it says proof. It says that H is either the cyclic group or the Klein 4 group, V. V is just Z2 cross Z2. Okay, so I'm good up to the lemma. Are you good up to the lemma?
Wait. He just said H is a group of order 4 and is therefore either a cyclic group of C of order 4 or the Klein 4 group that is C2 cross C2. Okay. I'm good with that.
Okay. So now the lemma is that at least one of the 2 subgroups got to be normal.
Mm-hmm.
So in other words, we cannot have 3 versions of H and 4 versions of K. Just looking at the picture, it looks like it's going to be a counting argument, which is something that we had to use in one of the other homework problems. problem 5b. So let's see if we can make it through that.
H turns out to be normal.
One of them is, oh, so if we assume that K is not normal, then we're going to show that H has to be.
Yeah.
Do you not use end of proof symbols? It's one at the end of the whole thing. I was just wondering where the lemma ended.
It ends, wait, wow. Oh, so the end of the proof is the end of the section.
So if K is not, maybe. Okay, so if K is not normal, then we know that there are 4 conjugate subgroups.
Right.
If we intersect 2 of them, intersection is either 1 or it's the whole thing.
Mm-hmm.
So if we get 4 distinct subgroups. Okay, so this is the argument that was used in that other problem 5b on the homework set. If we just look at the elements that are in the conjugates of K, then there are going to be 10 of them, right? 10? 9? 9. So if we take the 1 out, then that leaves 2 in each of the subgroups. There are 4, so that's 8, and then we have to put 1 back in, so that makes 9. Or there's just a little picture there. There's the little box at the very bottom of here.
Page.
There it is. I mean, that's the proof.
Right, yeah, that's...
On page 209.
Yeah.
Is the end of the lemma. I believe that. Here there are just enough elements left over to make one Sylow 2 subgroup. In the problem 5b, there were not enough elements left over, so it was showing that something was impossible. So here it is possible to have 4 Sylow 3 subgroups. If we do, then there's only one Sylow 2 subgroup. So it looks like we're able to break things into cases now.
Right.
One case is the abelian one, which is boring. The other 2 are going to be 3 Sylow 2 subgroups and 1 Sylow 3 subgroup. So 3 H's and 1 K. We can have 4 Ks and 1 H. And either way, since one of them is normal, K is always equal to KH.
Right.
Is that right?
Yeah. Alright, if you have K as normal, but H is not, then H operates by conjugation on K. Oh, he divides it into like so many cases. 3a, the case 3a is like when K is normal, H is not normal, and H is a cyclic group.
Oh. I'm working from a paper version of the book. Yours is more recent. Mine doesn't have any matrices in it. Yeah. Way back, there was like a science book club or something, and I joined it, and this was one of the books that I got.
Wow.
You could, if you sign up, you get 3 free books or something. So this is one of my free books.
Wow. They're giving art in for free.
Yeah, it was brand new at the time. I guess it was in the 90s because the copyright is 91. It was a new book. Okay, so case 1 is probably where they're both normal. So
Case
that
one,
means
yeah.
that E is just the product.
Yeah.
That's boring. We're good with
Mm-hmm.
that. So case 2 is when K is not normal. So that's my case 2 also in my
Yeah.
book. Okay, let's figure out case 2. So H is normal in G, K is not. So there are going to be
Mm-hmm.
3, no, there are going to be 4 conjugate Sylow 3 subgroups. K1, K2. So that's kind of the picture on the previous page. And G operates by conjugation on that set.
Mm.
Oh, okay. I was wondering why we're not just letting letting K operate on H. I think it's because he already knows what the answer is. So he's
Yeah.
trying to show that this one is A4, and then he's going
Yeah.
to move on.
Right.
Okay, let's use everything we know.
Mm-hmm.
So if you
Yes.
conjugate one Sylow subgroup, you're going to get another one.
Right, that's what it did.
How do we... Okay, I believe that that is a mapping from G into S4. How do we know that the image is A4?
You have to show that the you have something about the subgroup of S4 which would contain just 3 cycles. So anything from G would map to 3 cycles. And how does it map that? Well, let's see. So you consider the normalizer of Ki, so one of the K's conjugates. And the counting formula we know shows that the order of the normalizer is 3. Therefore, the order of the normalizer and order of each conjugate is the same. Now, the only element common in all the subgroups, Ki, is the identity, right? Now, if that's the case, the operation that we define for this permutation representation is injective. See, mm,
What's the counting formula again?
the counting formula was
The
about
order of the stabilizer times
There was some confusion about the stabilizer, normalizer, and the centralizer.
Yeah.
But so
If a group G acts on something, and is it the number of cosets isn't the word. What is it? Number of elements in the orbit times the size of the stabilizer is equal to the order of G?
Something like that. Wait. Right, so this is the counting formula. The order of G is equal to the order of the normalizer times the number of conjugates. We saw that in Rotman.
Okay. Order of G is the number of conjugate subgroups times the order of the normalizer.
Yeah, and the order of the normalizer happens to be, we got it as 3 because of the fact that we have 4 conjugates, and so 3 must be equal to
size of the normalizer.
Right.
Okay. Okay, I understand that sentence now. Oh, and since each ki normalizes is in it, since ki is in its normalizer,
yeah,
and k has 3 elements, then
yeah,
its normalizer is just k. So that means that if you conjugate by anything else, it's going to move it to a different one of the k's. So G inverse is equal to k if and only if G is in k. Is that what faithful means?
Here, I don't know, the operation of G is faithful means, I believe, this homomorphism well defined or something like that.
Let's see. Wait. I think faithful means that the only element which fixes everything is the identity.
Okay.
So the identity is the only element which stabilizes all subgroups.
But how does that make phi injective?
Because it's like it's the kernel of phi.
Okay, so the only things that get mapped to identity in S4 is the identity itself in G.
Yes.
Okay, so
there's
that's
nothing else that fixes all of these subgroups.
Okay, yeah, makes sense.
All right, we've made it through another sentence. Doing great. So now what?
G is isomorphic to its image in S4. Yeah.
Okay. So I guess we want to know how many subgroups of S4 have order 12. Okay, so since G has 4 subgroups of order 3, yes, it contains 8 elements of order 3. I believe that. So their images are going to be the 3 cycles in S4, which generate A4. So this is going back to that one day where you were talking about why A4 is not simple, because we know all this stuff about the being generated by the 3 cycles. Remember that?
Right.
I don't remember understanding it, but I remember you're talking about it.
Let's go back to Rotman.
If we agree that the 3 cycles generate S4, generate A4, then we're good.
Right. Because then you'd have to say that the image of G would would be A4 would be a subgroup. Sorry, I mean, yeah, it would be a subgroup of the image of G, whatever. But
I think we were looking at like even and odd permutations. So every 3 cycle is an even permutation. And there's probably some more or less straightforward argument that says that you can, if you've got any permutation with an even number of transpositions, then you can group those transpositions so that what you've got written is, you can write it as the product of 3 cycles.
yeah. Okay. Right, so this is A4. I don't know, I was like, this is A4 as, like, for some reason I was thinking about A5. A5, in A5, all your 3 cycles are conjugates. And there was a kind of
Yeah.
computational proof in Rotman, which we didn't go through. I kind of feel like we should have gone through that coloring thing in Rotman. Maybe it would have made more sense.
I don't know. Depending on the book, some of these books just seem to rely so much on cycles or some specific group.
Yeah.
Like Artin is going to be matrices and other stuff. Rotman likes those upper triangular matrices or unit triangular matrices. And other people just like being able to explain everything in terms of cycles.
Right.
I think I'm convinced by case 2. I think I'm good with that. If H is normal and K is not, then we've got A4. So that checks off 3 of the 5 different isomorphism types. So now let's see what happens if K is normal and H is not.
Right, if K is normal, then K is going to contain these things because of the conjugates.
Sounds good. We've got a couple of options for what H is. H is either going to be cyclic or it's going to be Z2 cross Z2. So for him, case 3A is when H is Z4. And I guess case 3B is when H is Z2 cross Z2. Okay?
Right.
We're going to say that H is generated by X. So K is 1y and y squared, H is 1x, x squared, and x cubed. And now we're going to look at how H acts on K by conjugation. Okay, so when H acts on K, action is going to be determined completely by what X does.
Right.
If we know what X, K, X inverse is, we'll know what X squared and X cubed do as well. So if we take X, Y, if we know what it does to Y, we're good, because then we'll know what it does to Y squared. So we just need to know what happens with the generators. X, Y, X inverse cannot equal 1, because that would mean that Y equaled 1.
And that's not possible.
X inverse can't be Y, because that would mean that H was normal.
Mm-hmm.
It would mean that everything in H commuted with everything in K, and we're
Mm-hmm.
assuming that that's not the case. So the only possibility is that X inverse equals Y squared, which is what he's saying.
Right.
So you know that X to the fourth is 1. He's listing relations here. We know that X to the fourth is 1. We know that Y cubed is 1. And we know that XY equals Y squared X. So there might be additional relations, but if we're in case 3, we know that at least those 3 relations hold.
Mm-hmm. Mm-hmm.
Oh no, this is case 3A, because we assume that H was cyclic.
We did.
So here they say, he says these relations determine the multiplication table. So these are all the relations. So there's at most one isomorphism class of such groups. Right. So it'd be possible to write down a set of relations which ruled out all possibilities. But there's no group with those relations. So we've got to show that this is actually a group.
Yeah.
And see, in the old edition, he didn't bother doing this with matrices, and in the new edition, he does.
Right. With the time, he.
Yeah, okay.
uh,
So is this is not the dihedral group. That's going to be the other one, right?
yeah. So wait.
So this is the one that he just gives using a presentation.
Mm-hmm. Right. I think like this
Oh yeah, there it
theorem
is. This
he
is number
has.
5.
Right. Yeah. Okay. So case 3b is when K is normal, H is not normal, and H is isomorphic to Z2 cross
Klein for a
Z2.
group.
Yeah, the Klein for. The stabilizer of Y for the operation of H by the conjugation on the set Y squared as order 2.
So in the old book, the way that he argues that these relations actually do define a group is by referring forward several sections to the Todd-Coxeter algorithm,
Ouch.
which is like 6 pages that I don't want to read right now. So maybe in the new edition of the book,
He has Todd-Coxeter.
yeah, but maybe in the new edition, if you can show that this is isomorphic to a matrix group, or to like a subgroup of a matrix group, then you're done. You said, well, look, here's the group. Other than just saying there is an abstract group which satisfies this. So what's his newfangled argument?
I don't know. Let's look at the stabilizer.
Oh, wait, there it is. So he's saying within the 2x2, this SL2C, these are complex 2x2 matrices with determinant 1.
Yeah.
So he's exhibited an X and a Y which satisfy these relations. So if we could just show that How do we know that those generate a group of order 12? Short of writing down their products. I mean, they clearly satisfy. What do we get when we square x? -1, -1 on the main diagonal. So x to the fourth equals 1, y cubed equals 1, because omega is a complex cube root of unity. And it's just it's just matrix multiplication to see whether xy equals y squared x.
Yeah. Wait. Yeah, essentially.
Oh well, if x to the fourth equals 1 and y cubed equals 1, and that means that there are at most 12 elements. So if you just show that there are at least 12 elements, then that gives you the order 12.
Mm-hmm.
And to show that it's a group, you just need to show that it's a subgroup of the bigger matrix group, which means you have to show that it's closed under multiplication and inverses.
Right, so you just show that it's a subgroup of the simple, not simple, it's a special linear group.
Special linear.
Yeah.
And the inverse of x is x cubed, and the inverse of y is y. Y squared. Okay, I like his new proof much better than having to go figure out what the Todd-Coxeter algorithm means. What do you think? I'm good with 3A. Are you?
Yeah.
Okay.
3B.
Let's look at 3B. Okay, 3B is when K is normal in G, H is not, and H is isomorphic to Z2 cross Z2. So now H has got two generators.
Mm-hmm.
Okay, so I'm guessing that we're using that counting thing again.
Yeah.
So what is the stabilizer of Y?
So
Of order 2.
the stabilizer of Y, if you remember, is the set of elements from G that you can use for conjugation for whatever you're taking the stabilizer of, right? So essentially it means, wait, no, that's the normalizer maybe.
I think the normalizer is just the stabilizer when you use conjugation as
Yeah,
your group action, right?
exactly. Right.
Yeah. The stabilizer of Y.
Is all the elements in G such that, so if we have, like, let's say all the elements Z in G such that Z inverse gives you Y back. Z back. Sorry, Y back, yeah. We're taking the stabilizer of Y, so. I believe it was in Rotman.
Okay, so we're looking,
Yeah.
we're letting H act on the set Y squared.
Mm-hmm.
Conjugation. So it's not acting on a subgroup, it's just acting on the set Y squared. We want to know what the stabilizer of y is.
Right.
So there are two conjugacy group or conjugacy sets, whatever. Either when you conjugate, you're going to get y, or when you conjugate, you're going to get y squared. So orbit has two elements in it. And the order of h is 4, so that means that the normalizer or stabilizer or whatever is going to have order 2.
Mm-hmm.
So I understand that sentence. The stabilizer of y is order 2.
Yeah.
So that means that we have an element other than the identity, one that commutes with y, and one which, when you conjugate, you get y squared. We know that each has at least, well, we know it has at least 2 elements. It has 4, but it has 2 non-trivial elements. One of them we're going to call z, which gives us the relation xz equals zx. And wait a minute. No. zy equals yz. And also an x, so that xy is y squared x.
Yeah, we just...
So x and z are in
H.
So H contains 1 xz and presumably xz.
Yes.
And H is abelian, we know that. So xz equals zx.
Yeah.
So that gives us all these relations.
Mm-hmm. Okay.
And then, obviously, that's D6.
No, don't tell me. I don't know anything about D6. I hate these things, like the symmetric group, the cycles. No.
Okay, so one thing that we can say is that this is a fifth. Oh, actually, we can't. So the question is, we've just written down a bunch of relations. The question is, does this actually define a group, or is there no group that has all of these relations on it? So I guess one way of arguing it is, you know that there's at least one group of order 12 that has not been taken care of by any of the other cases, and that's D6. And this one that we just came up with, case 3b, is also different from all of the above. So it's got to be D6. This was the last case. There are no other groups, and we haven't gotten to D6 yet. So this weird thing's got to be D6. And I am not going to write down a multiplication table for it to check it.
I mean, the relations
Oh,
make
that was
sense.
fun.
Yeah, because like the relationship, you think about it, like H is abelian, so X and Z are from H, so X squared is equal to 1, Z squared is equal to 1. Y cubed is equal to 1 is because of the action, alright? And we chose Z such that YZ is equal to ZY, XZ is equal to ZX because it's abelian, X and Z both are in H, and XY is equal to Y squared X because of our choice of X. So, yeah.
One thing is that it kind of feels like a way of figuring it out if you already know the answers.
It's fabricated. It's art and it's fabricated.
It's like case 2. there's no justification for why
We need
we
S4.
consider, why is it that we're going to let G act on H?
Mm-hmm.
Because in the next one, we let H act on K or something. And in the third one, we let H act on the subset containing Y and Y squared.
Yeah.
For these group actions, it's like you have to fabricate one for each different case.
Yeah.
And I guess the only way you know what's going to work is by trying a bunch of different ones. Of course, what we're not seeing is all the things that he tried before coming up with the most elegant way to do it and put it in the book.
Wow. You have to learn it from Martin.
It's even like what we see between the two editions.
Mm-hmm.
It's like case 3A, he thought he had one explanation, then he came up with a better one, so he changed it between
Yeah.
editions. So I guess what I'm complaining about or whining about is that it doesn't give you a real blueprint for how to attack problems. It gives you a few strategies, but unless you already know what some of the answers are, it's hard to see how you would choose a strategy. So now with the whining over, you want to attack either order 18 or order 20. See if we can apply some of what we did.
18 seems doable. Let's see. If 18 is doable, I think 20 is. 20 follows from there. We can just say that.
So he didn't list these in strictly increasing order. He gave 33 first, which was obviously the easiest one. Then he
Yep.
gave 18 before the others.
Mm-hmm.
So I'm going to make the possibly false assumption that 18 is easier than the other two, or has fewer cases to look at or something. How about if you talk? Tell me about how many Sylow subgroups possibly there are of each order.
Hmm.
I'm going to mute myself for just a second because I'm
Okay.
going to refill my coffee. It's noisy in there. I'm still listening.
So, yeah, we have, yeah, 18 is 2 times 3 square, of course. So, we have, a Sylow 2 subgroup. We have, right, we have at least, one Sylow 2 subgroup and two Sylow 3 subgroups, something like that. Right? Hmm.
So how many Sylow 2 subgroups can we have?
I would say that we have one of Sylow 2 subgroup and two Sylow 3 subgroup. Ah.
Let's see. Let's use H and K again.
Mm-hmm.
So we'll let H be the name of the Sylow 2 subgroups,
Yep.
and K can be the 3 subgroups. So now let's apply that counting thing in the Sylow theorems, number 3 or whatever, to see how many there can be of each. So the number of 2 subgroups, the number of H's, has got to divide 9.
Right. The number of H's.
And It's got to be congruent to 1 mod 2.
One mod 2, yeah.
The number of 3 subgroups has to divide 2, and it's got to be congruent to 1 mod 3.
Doesn't look possible.
For K, there's only 1, right?
Yeah.
So that's the good news, right? There's only 1 free subgroup. Which has order 9. So we know that K, since its order is the square of a prime, it has to be abelian. So K is either Z9
Or Z.
or it's
Decline.
3 cross Z3.
Z3 cross Z3 is isomorphic to
what?
Z9.
I don't think so. It doesn't have any elements of order 9.
Doesn't? It's so Rotman, God.
No. Okay, so unfortunately, it looks like we can have a bunch of 2 subgroups. Number has to divide 9, and it has to be congruent to 1 mod 2. So that could be 1, 3, or 9.
1, 3, 4, 9, yeah.
Okay, so again, the good news is we know that the free subgroup is normal. There are 2 possibilities for it. The 2 subgroup, which has order 2, so it's simple.
Yep.
It's either 1 of them, 3 of them, or 9 of them.
Hopefully it's not 9.
Hopefully it is not 9.
So if you have 1, which
If we have 1, we're in great shape, right? Because then H and K are both normal.
Yeah. You have Z3 cross Z3.
And they commute. Let's go ahead and write that down.
Yeah. Case
Case
1.
H is normal in G. And we've got either Z2 cross Z9, which is Z18, or we've got Z2 cross Z3 cross Z3.
Yeah.
Which is Z3 cross Z6, but whatever. Okay. So case 2 is going to be when there are 3. So H1, H2, and H3. So now is when we're supposed to come up with some action of some group on some set. And you apply some counting argument.
Damn. Martin just pulled things out of the hat and showed us, but we don't have a hat.
Yep.
So we need, wait, H is our 2 subgroup right here.
Yes. And we know that K is normal in G.
Alright, K cannot be normal.
No, K is definitely normal.
Okay, K is normal, okay.
But we don't know whether it's Z9 or Z3 cross Z3.
Okay. Okay.
So this might be where we have to look at case 2A and case 2B.
Mm-hmm.
So case 2A, I'm guessing the cyclic one might be the one which is easier to analyze.
Right.
Then K just has one generator.
And
So we say that K is generated by some element X.
And we can show that the order of that element is 9.
Yep. It gives us one relation. We know that X to the 9th equals 1. And now we could let K act on a set of conjugates of H, right?
Okay.
We could just let K act on the set of conjugates of H.
That is H1, H2, and H3.
Mm-hmm.
We don't have luck with any of the symmetric group here, otherwise we could have made the same argument as Artin.
Right. Because the symmetric groups, they all have order n factorial, and the alternates are n factorial over 2, right? So 18 is not a factorial, and it's not half of a factorial. So we don't have to worry about those. Okay, so if K acts on a set of conjugates of H by conjugation, we know that there are 3 elements in the orbit, H1, H2, and H3. Order of K is 9. So that means that the size of the normalizer of, say, H1 is 3. And the normalizer of H1 is a subgroup of K?
Yeah. It's a normal subgroup? Yeah.
So the only subgroup of K of order 3 is going to be the subgroup generated by X cubed.
Okay.
So if H1, which has order 2, is generated by Y, and that means that X cubed has to commute with Y.
Yeah. Okay.
So what do we have so far? We've got 2 generators, X and Y. we have three relations. X to the ninth is 1, y squared is 1, and x cubed y, yx cubed.
Mm-hmm.
Wouldn't it be nice if that defined a unique group of order 18? Even better if it's something familiar, right?
Mm-hmm, mm-hmm.
It's like there's got to be more to it. Oh, well, if x cubed is the normalizer, then that probably means then that xy x inverse is going to generate, say, h2, and x squared y x inverse generates h3.
Wait, Damit gives as an example. I think we can continue because we're doing progress, but Damit gives on page 144 groups of order p squared q. Both the cases when p is less than q and p is greater than q. And his
Sorry, which page?
144 and 145.
All right. So this is, in this chapter, he's just counting subgroups, right?
Oh, damn. He has the case when p is equal to 2 and q is equal to 3.
And let's look at it.
Right, so the example, there are two examples in page 144, and the first one is of what we saw in Artin, yeah.
Order 12, right?
Yeah. The same proof, exactly, nothing different.
Looks briefer, which isn't necessarily good.
But the second one is about p squared q. So this will solve 18 and 20 for us. I'm not sure about the notation. Is NP here like order of P, that is N or something?
I think it's the number of Sylow subgroups of order Q. It's the number of Q Sylow subgroups, Sylow Q subgroups.
Ah, okay, the set of Sylow P subgroups, okay, of G. Okay.
Do like this notation of SYL sub P of G.
Mm-hmm.
That you have a symbol for the set of Sylow subgroups of.
Right.
Okay. So we're going to look first at when P is bigger than Q. So is that the case? That's the case we're looking at now, right? That's 18.
No.
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 18 is 2 times 3 squared.
Right. We need P to be less than.
That would be P equals 3 and Q equals 2.
Well, if we are in the same order, then
Yes. Yeah.
Yeah.
This is what we said.
Mm-hmm.
This is like us saying that K is normal.
Mm-hmm.
So, okay, we're going to check that off. That agrees with what we just did. Now, on the other hand, what happens if P is less than Q? That's like 12, the previous example.
Yeah. Right, so he assumes that there is one one Q Sylow Q subgroup, and then Q is going to be normal in G because Q is the only Sylow Q subgroup. Assume therefore that NQ is greater than 1, so if this is 1, then you have Q as normal, so our H and K both are normal. So that was the case, right? We had like case 1 of ours, right? We had 1, 3, 9, we chose 1, right?
If it were 1, then it was normal.
Yeah.
And that meant that it was abelian.
Yeah.
And then we were moving on to look at 3 and 9. So it
Yeah.
moved up to 3.
Right, but he decides that you don't really necessarily have to go to 3. Says if your NQ is greater
Well,
than 1.
notice right there, it says, so NQ is either P or P squared. So that was the 3 and the 9 that we were just considering.
Yeah, exactly, yeah.
Ooh, look at that. It says since Q is bigger than P, you can't have N of Q equals P. Oh, that's because this is the case P less than Q. That's not what we were looking at.
Yeah, this is
We
P
were
less
just
than
doing the
P.
case P bigger than Q.
Yeah.
So if Q is bigger than P,
the number of Sylow Q subgroups cannot be the same as cannot be equal to the prime.
What is T? Okay, there's TQ.
Right, he's saying
TQ is P squared minus 1. It's Q is prime.
right, Q divides either P minus 1 or P plus 1. The formula is impossible. This looks like a number theory proof.
Right.
Since Q is greater than P, but Q divides P plus 1, we must have Q is equal to P plus 1. Of course.
And the only two primes which differ by 1 are 2 and 3. We've already done groups of order 12. Yeah. But this is still just counting them. Classifying is going to happen in section 5.5, like around page 181.
181?
Yep.
Oh, yeah. Damn, this table.
So down at the bottom, it has order PQ. 183 is P cubed.
Oh, wait. So the only stuff for 18 is Z18, Z6 cross Z3 when we have abelian, right? So that's our case 1. Non-abelian groups are S3 cross Z3, D18.
Oh, that table.
Well,
I was looking at the book, it wasn't looking up. 1, 2, 3. So you should be able to find 3. I wonder which one this is that we've been picking at. I'm guessing it must be D18. Because neither of the others have elements of order 9. D18 does, right?
I don't know what D18 looks like, so don't ask me.
It's the symmetries of, I think, a nonogram or nonagon, something with 9 sides, a 9-sided
Okay.
polygon, regular polygon. So that is generated by rotation by 2 pi over 9 and reflection across the x-axis. So if you think of the 9 vertices equally spaced around the unit circle with one of them sitting at the origin,
Mm-hmm.
then the dihedral group is going to be generated either by rotating the dot at the origin to one of those other guys, or by reflecting across the horizontal axis. If you make them complex numbers, it'd be either multiplying by e to the 2 pi I over 9, or by complex conjugation.
Do you see this pattern?
So that's the D18. So that's got to be what we've got.
Yep, yeah. For order 8, you have 5 classes, and it has D8. For order 12, it also has 5 classes, and it has D12. For order 18, it has 5 classes, and it has D18. For 20, it has 5 classes, and it has D20, and it all looks the same to me.
I don't know how to predict the 5s. I mean, the Ds are always going to be in there.
Mm-hmm.
Or anything that has even order, that's going to be somewhere on the list.
Mm-hmm.
I guess there are so many abelian groups of order 16 that they didn't list them. That was that formula that you just saw, right? Remember you saw the thing with p to the 6th?
Yeah.
This is only p to the 4th, but apparently there are so many of them. It's not going to try to squeeze them into the box.
Damn these groups. So for 30 we can just say that, Damit has done it, so just learn it from there. It's pretty detailed.
Yeah, I mean, this is kind of what we were saying when we first started off. You can't fast track through stuff like this.
Yeah.
If you wanted to stay at an abstract level, then you can say, okay, you recognize that the Sylow theorems allow you to do this stuff.
Yeah.
If you're actually going to build the skills of being able to do it yourself, you just got to slow down, and you just got to decide, is it even worth it?
Yeah.
Where we're trying to go, is it important that we're able to classify groups of order 18? Then the answer is probably not.
No.
It's plenty interesting, and I envy anybody who's decided to slow down and do it as long as they keep going. But I think we can justify saying we spent some time thinking about it, that we have things of higher priority that we want to get to.
Yeah, and I mean, we did a fairly good job considering the amount of things the thing is, when you're doing group theory in undergrad, they'd never touch the Zasenhaus lemma, as far as I can tell. So, and we spent a whole week on that, and we have problems of that. We haven't touched it.
When I did do the undergraduate algebra, we did spend time on the Sylow theorems and classifying groups. Obviously, I don't remember much of what I learned, but at least sometime in the past, I can say I spent time on it. I think I know enough that I think I know a lot of what I don't know. I mean,
Yeah.
I can identify the things that I would need to study if I wanted to be able to do this.
Okay, yeah. I mean, you know where to look and also what to learn.
Yes. Okay. One thing is these semi-direct products,
Mm-hmm.
which is basically figuring out how one subgroup acts on another by conjugation.
Okay.
Then when you're creating those, or when you're trying to give a complete list, every time you let one of these subgroups act on the set of conjugacy classes of another subgroup, and that lives in the in a certain automorphism group. Because
Okay.
even the stabilizer, which leaves the group fixed, is going to rearrange things in there. So you need to know more about automorphism groups.
Um,
There's, I know, if I wanted to plan out a week of getting good at this, I think I would know
mm-hmm.
what to do. But
Okay.
a week from now, we're going to be doing
Modules.
semi-direct products of modules. So, so I'm going to be studying modules instead.
Mm-hmm, mm-hmm.
So it's already been about a little over an hour and a half. Are there others on this list that you at least want to talk about a few minutes before we break?
Let's see. The Bourbakis doesn't look like something we can do now. The third problem from Herstein looks interesting. Let's see that. Herstein, so you have a P Sylow subgroup, and A and B are in the center of P. A is the conjugate of B with respect to some x. You have to prove that there exists a y in the normalizer of B such that A can be the conjugate of B. And I
So if A is
believe,
the conjugate of B
mm-hmm,
in the big group, and it's actually a conjugate of B
the
in the
normalizer.
normalizer of P, we're assuming that A and B are in the center.
Yeah.
But when I was unsuccessfully thinking about this, I tried to draw a tower of groups.
Mm-hmm.
So the groups involved are P, G, normalizer of P, and the center of G.
Center of B.
Oh, center of P. So Z of P. And somewhere separately, we might also be considering the subgroups generated by A and the
Mm-hmm.
subgroup generated by B.
Mm-hmm.
Just with those first four, P, G, normalizer of P, and the center of P, out of those chain from top to bottom, G's on
Okay.
the top. Normalizer of P is bigger than P, right, in general.
Right. Normalizers are
P is
bigger than.
smaller than that,
Yeah.
and the center of P would be down at the bottom, above 1.
Okay.
So when I'm drawing my chain, I've got G at the top, then the normalizer of P, then P, then Z of P, and then 1 at the bottom. And
Okay.
A and B are in Z of P.
Wait, what is Z of P? In center, right?
Center.
Okay.
Isn't that the
Yeah,
notation?
notation, yeah.
I guess it depends on what book, right?
Hmm. I kind of have a hunch that Herstein is using conjugacy class.
Mm-hmm.
Where is this problem from? Oops.
So there's an element of G if you use that X to act on P, it's going to take A into, or B into A.
Yeah, B into A.
We want to show that there's an element in the normalizer of P which takes B into A.
Right.
Presumably that's not always going to be true. It will be true if A and B are in the center of P.
So the center allows you for commutativity, and the center is a normal group, a normal subgroup.
Mm-hmm. And the normalizer of P is normal in G, right?
Yeah.
I'm guessing P is not necessarily normal in its normalizer.
P is not normal in its
Oh
normalizer.
yeah, or is it? Normalizer is everything, or all the elements that commute with P, right?
Mm-hmm.
So that would make P normal in its normalizer, right?
Yeah.
So is it true that the normalizer is a normal subgroup of G? Or is that the part that's not necessarily true?
I don't think N of P. Let's look at Rothman. He had the notation, I believe. Right here. So the subgroup, this subgroup of G, right? So it's a subgroup of G. It's the, but it's a normal subgroup.
When you started talking about normal subgroups, it made me think that maybe we should be taking quotients somehow.
Yeah, I was thinking that too.
Then the other thing is, should we
can
just be
use
looking at conjugacy classes?
right, and the third Sylow theorem has something to do with the conjugate. Sorry, quotients. So, if you consider a normal subgroup Wait, isn't center the largest normal subgroup? Or something like that?
I want to say no.
Let me check.
In a non-abelian group, the center is trivial. Or can be trivial, right? Is the alternating group normal in the symmetric group?
Yep, just like the special linear group is normal in the general linear group.
The center of the symmetric group is just the identity, right? The only thing which commutes with everything is the identity. So
Right, yeah.
the center's not the biggest.
Yeah, it isn't. It is a normal subgroup, but it is not the biggest.
Every subgroup is normal in its normalizer.
Is that
If I'm reading Hungerford right,
Hungerford?
clearly every subgroup K is normal in its normalizer.
Okay.
If you don't believe it, he's going to bully you into believing it. Clearly it's true. So this thing that we're trying to prove is that if there's an X in the big group that has this property, and we want to show that there's a Y in a smaller group that has the same property, that's making me feel like there is some kind of equivalence relation going on. The X and Y are equivalent in a certain sense. And we could create an equivalence relation that X twiddles Y if X times B times X inverse is equal to A. We want to create an equivalence relation so that everything that has that property
Like, okay,
is in the same equivalence class.
Yeah, we can take it out.
And then what we'd be trying to show is that within that equivalence class, there's an element which is in the normalizer of P. Every equivalence class has a representative in of P.
It's kind of weird because I don't know, this XBX inverse so we have to prove that there exists a Y in the normalizer such that Now you can have the conjugate respect to that. So if we like do contradiction, so there are no y's in the normalizer, so nothing in the normalizer can let you have a conjugate, which means that wait, did you say that like P is a normal in N of P?
Yes.
Okay, so P is
I'm
normal.
gonna need to. Headphones are dying.
Hmm. Damn. I'm trying to figure out which Sylow theorem we can just use using this normalizer. Doesn't look that straightforward to me.
Can you hear me?
Yep.
Okay. I had to take the headphones out.
Hmm. Alright. So, when a group G acts on itself by conjugation, then the orbit is going to look something like this. And it's the conjugacy class of X. Here, I believe if we have G acting on the center of B, G acting on the center of B, then you take some element of the center, that is A, so A in P, such that A is equal to some, I don't know. That's just a while. So again, if we have a y, so what does it mean to have a y? So if y is in the normalizer, it means y and y inverse gives you n back. Sorry, y inverse gives you p back. Right.
Yeah, so the element x, it takes b to a, but it doesn't necessarily leave p fixed. Y does.
Yeah.
So in a way, this is saying is that if you have some element which takes b to a in the bigger group G, and there's a way to find another element which does the same thing but leaves all of p fixed.
Yeah.
This almost has a topological feel to me with constructing a function that has an action just in a neighborhood of a point while leaving everything outside of it alone. It's a common thing in, well, geometry and differential topology, using these bump functions and stuff to create functions that do specific things in a small area, leaving everything else alone. Like to patch two functions together smoothly, things like that.
How do you use the fact that it's a Sylow subgroup into all this information with normalizer and whatnot?
Sylow 3 subgroups. And let's say that they have order 27. And they have non-trivial intersection? I guess is that the answer is yes. If I let this x act on p, oh, and it's going to leave the center unchanged, right? Because the center commutes with everything.
Yeah.
So the center of one p-Sylow subgroup is going to be the center of all of the p-Sylow subgroups. Is that right? I think it's right. In fact, it is going to be the intersection of any two. No. It should at least be this intersection of all of them. But maybe not the pairwise intersection. Because if I've got two p-Sylow subgroups, let's call them P1 and P2. then P2 is going to be x P1 x inverse for some x in G, because any two P-Sylow subgroups are conjugate.
Okay.
But anything which is in the center of P1 doesn't move when you conjugate it. Wait, but does that... So if you're in the center of P1, if A is in the center of P1, then since P2 is going to contain XA X inverse, which is just A, that means that A is in the center of P2 as well. I guess that I'm at least convinced that P1 intersect P2 contains the centers of both P1 and of P2. That's wrong. That's wrong. I don't know if it's wrong or right. I think I'm confused about center versus centralizer. Center. The center of P is everything which commutes with everything in P.
Right, so again...
So XA, X inverse is not... It doesn't mean that A has to commute with things that are in the big group G. So I take back what I was just thinking. So I'm back to being confused about what happens to the center under conjugation by something in G.
So in center, elements, the conjugation class of every element is the element itself. There is nothing else. Alright, so no element in G is conjugate to any element in the center. Rotman states that, yeah. God.
So if we use this element x that we've got, we know that x p x inverse is going to be possibly the same, possibly a different Sylow subgroup. Just know we know it's going to be a Sylow subgroup. What do we know about x z x inverse if we call the center of p z? What does conjugation by x do to the center of
Conjugation
p?
of the center.
We know that it takes b to a.
It is going to be the same because it's normal.
Well, it's not normal in G necessarily, right?
Center of P.
Right now our x is drawn from G.
Oh, yeah.
The center piece, yeah.
Ah,
I would like to think that it's the same. I don't know what that would give me, but it feels like it would give me something to work with. I kind of want to feel like if conjugation by x fixes z, maybe conjugation by something in a smaller subgroup might fix p. I do know that. I mean, conjugation by y, conjugation by something in n fixes p. That's just the definition of the normalizer. But I want to move down, fix p, while preserving this action of taking b to a. Something I wrote down on my tool list that we haven't yet worked with is the subgroups generated by A and B. If that makes any difference.
Can X be in the center of P or centralizer? Wait. What would the centralizer of X look like? No, it would not give us anything. Centralizer of B. Right? Centralizer of
Did you see
B.
something?
Yeah?
I remember seeing some exercise about the normalizer of the normalizer.
How?
Is that ringing a bell for you?
Maybe.
Like
Your
the
audio
normalizer of the normalizer of a certain group is the normalizer.
Yeah, I'm not sure.
It could be that the normalizer of P is normal in G. Seems like something that was an exercise, not a theorem or something mentioned.
Well, we can
in
use
the
an
text.
exercise as a theorem.
Normalizer. I know. 123. How's it going? I just looked up a normalizer of the normalizer of a Sylow P subgroup, and there's a question about it on Math Stack Exchange.
What does it look like?
And it is true that the normalizer of the normalizer of P is the same as the normalizer of P.
Right, if you think
And
about
it's
it.
in all kinds of different books.
Ah.
But it uses the fact that it's a Sylow P subgroup. I don't think it's true in general.
It's not true in general?
It's in Jacobson and Herstein. Not for just a subgroup. It's true for a Sylow subgroup.
What condition from the Sylow does it use?
I'm trying to look at the proof.
Ah.
Ooh. Wonder if you can find that. I'm not looking where you're looking right now. Try a search on normalizer of the normalizer of P. See if you can find the same article I'm seeing.
Normalizer of the normalizer of the... Okay.
That's the one.
Let's see. This is an exercise from Prolay. This was the question on 1995 Columbia Algebra Qual. Okay. This is the first exercise on Jacobson.
It's full. Thanks. So look at the answer there. Because that's giving me a feeling. It seems to share a flavor with what we're working on now.
Indeed.
So P is a Sylow P group.
Of N of
So it's got
P.
highest prime order and of N of P. So if X is in the normalizer of the normalizer of P, does that next line make sense?
He says the XP X inverse, the conjugate with respect to X, is a subgroup of the conjugate of the normalizer with respect to X. And that is equal to the normalizer because that's what the normalizer is. Okay, no, that's because the normalizer isn't the normalizer of the normalizer. Wait, n of p is in the n of p, right? And we're taking x from there, so this turns out to just be n of p.
Okay.
But p groups, Sylow p groups are all conjugate. So we can take a y from the normalizer of p, and say that the conjugate with respect to y is going to be equal to this, the conjugate with respect to x, because they're all conjugate. And if you're taking something from the normalizer of p, it means y inverse is going to be p, right? Thus making x p x inverse to be p, thus showing that x is in the normalizer of p.
The part that's feeling relevant is starting out with something, an x, which is in the normalizer of the normalizer, and using that to find something that's just in the normalizer. It feels like we're trying to step down in a similar way. Does that make sense?
Yeah, I believe so. The main thing we're taking away from the Sylow whatever is that Sylow subgroups are all conjugate, right? That's what we're going to use. Now, I don't know, wait.
So what we haven't used, that this proof is using, is that our group P is not just a Sylow subgroup of G, it's also a Sylow subgroup of its normalizer. I don't know if that helps us.
Yeah.
But a direct result of this is, since the normalizer of the normalizer is itself, it means that the normalizer is a normal subgroup of G.
Yeah.
So in this chain we've got, with G at the top and 1 at the bottom, this is actually a normal series, right?
Wow.
1's normal in Z, Z's normal in P, P's normal in N, and N's normal in G. So can't we just say this is obvious by Jordan Holder or something?
Oh wow.
It's a direct result of Jordan Holder. I'll leave the details to the reader.
Wow. Hurstin hasn't even mentioned Jordan Holder, and you ahead of Hurstin. So that was helpful. That was a nice thing. Think about normalizer of normalizer. I didn't even think it would be a thing.
Here's a question I think is related. I think if we could solve this one, then we could solve the bigger problem. What if we chose a point C in the center? And suppose that we had an X in the big group. which fixed C by conjugation.
Okay.
So x, the x inverse is just equal to C. Would we be able to find an element of the normalizer which also fixed C?
Wait, x inverse is some element of the center.
Yes, C is an element of the center,
Mm-hmm.
and x inverse equals C.
Okay.
In other words, x is in the stabilizer of C. Or, yeah, so if x is in the stabilizer of C, is there also an element y of normalizer of P, which is in the stabilizer of C?
It was just like the problem previous to what we were doing, the normalizer of the normalizer.
Hmm.
The world is round. Damn. I'm trying to find a way for contradiction, in the sense that, like, your x that you're taking conjugation with respect to can be in G, but it cannot be in the normalizer. Right? So I'm trying to contradict that. What it is from the normalizer that would contradict. This feels doable. Wait. So AB is in the center of B. That means AB is equal to BA. So if we try to find the conjugate of AB with respect to x, that will be xAB x inverse is equal to xBA x inverse. Now xB x inverse is just A. So conjugate of AB with respect to x is equal to A squared. I don't know if it would be a funny news.
I was writing stuff down. I believe that the conjugate of A by X will commute with the conjugate of B by X.
I believe so too. Hmm. Um.
I'm just going to prove that I still don't fully understand that counting theorem about stabilizers and orbits.
Mm-hmm.
Here goes. If we let G act on P, if we let G act on P by conjugation, then that's going to give us a list of all the Sylow P subgroups, because they're all conjugates.
Right.
The normalizer of P is the stabilizer of P. It's everything that leaves P alone.
Yeah.
So if I make my list P1 to Pn, I can just assume that P is the first one.
Mm-hmm.
And then the number of different subgroups is going to be the order of the normalizer in G.
How's that?
So does that mean I can think of G mod N of P, since we now know that N of P is normal in G, that G mod N of P is going to be I want to think about, I can make G mod N of P act on the Sylow subgroups, and everything that leaves P fixed is contained in that normalizer.
Mm-hmm.
So I want to say that that action of the quotient group doesn't leave anything fixed. So it would be a one-to-one map. There's a one-to-one mapping of that into the symmetric group on the N P subgroups. Kind of like that argument we saw earlier.
Yeah.
I don't know that that helps at all. I'm just trying to understand what this P does. Why we have the normalizer in the chain.
Damn.
It also feels profoundly unhelpful because I'm trying to say that it shares a quality with something that's in the normalizer. So modding out by the normalizer seems like a bad thing, because then I'd be trying to argue that something in G was actually in N of P, and it's not. We're not trying to show that X is in N, but rather that it's equivalent to something in N. If we're using some kind of quotient group, I don't think we're going to be quotienting it out by N of P.
Mm-hmm. Hmm. What if we take the conjugate, normalizer of the center?
The normalizer of the center of P in G.
Yeah. The center of P is already normal in P.
Yeah, but not necessarily in G.
Yeah.
So it would make sense to take its normalizer.
Well, I remember because in the centralizer, all the conjugates are themselves, right? Oh, okay, I'm totally confused now. I'm talking about the center, not the centralizer. Um, but, yeah. Yeah. Mm, mm, mm. Ah, so the normalizer of the center means you have y inverse would give you z back. So what is it that would like right. Mm, mm, mm. Do you realize that x cannot be in the center?
Center of what?
P?
Right. Because if it were in the center of P, it would be fixed. It couldn't take B to A, right?
Mm-hmm. I have a hunch that P is going to be a subgroup of the centralizer of either A or B. I feel it's A, I'm not sure about B.
I think I was somewhere in the same neighborhood. Something I just wrote down is that if I start off with P, which contains both A and B, and I conjugate by X, I'm going to get another Sylow subgroup, but the new Sylow subgroup still contains A, since XB, X inverse is A. So that means that those two subgroups, E and P prime, both contain the subgroup generated by A. That's not what you're saying. You're suspecting that you're wanting to look at just the centralizer of the single element A. Or that's Z of P certainly leaves A and B fixed. So the stabilizer of the element A is at least going to be somewhere between Z and P. And it does not include X inverse, since X inverse moves A to B. Which means it's not going to extend up to N of P, because there's some Y in N of P, which is going to move A and B around. So it's at least as big as Z, and it definitely doesn't extend all the way up to N.
Damn, this is an interesting problem. This is like just like 1 star. He has like 2 and 3 stars. I don't know how hard they're going to be.
I wonder whether we pulled all the tools out of the toolbox. If we've got everything it needs. Presumably you've seen it somewhere, but are we thinking of everything that is going to be helpful? Did you look at the previous problem
You're right.
in Herstein?
That's the one we saw.
It's like, is this a simple follow-up to the one that came before? Oh, look, that is that one. Look.
Alright.
It's showing that the normalizer is the normalizer.
Right, and that's why I
So
said
maybe that's not a coincidence.
the world is small, round, sorry.
Oh. So maybe the idea used in that is important for number 18.
Mm-hmm.
So I'm just trying to abstract it again. Let's say that I know you hate matrices, let's say that we have some linear transformation of R3,
Mm-hmm.
which takes I to j. It takes the unit vector in the direction of x-axis into the unit vector in the direction of the positive y-axis.
Mm-hmm.
So let's say that we've got a group of transformations on R3, and inside that group there is an element which takes I to j. Then we want to prove that there is a transformation that takes I to j and also leaves the xy plane fixed. That's not quite right. But I think that's kind of the flavor of what we're trying to do.
Mm-hmm.
We've got a mapping which takes one Sylow subgroup to another one and simultaneously moves B to A. And what we want is something that leaves that first Sylow subgroup fixed and moves B to A.
Yeah. Ah.
So we're
Mm-hmm.
given, here you go, here's an element that takes B to A, but I want you to do, and by the way, you know that is going to take the Sylow subgroup it's in to another Sylow subgroup. I want you to accomplish the same thing, but not move out of the original Sylow subgroup. I want you to find a Y that leaves your Sylow subgroup fixed, still moves B to A. Oh, so to make my earlier analogy correct, I want a mapping from R3 to itself. It takes I to J and leaves the Z-axis fixed. So my original one might take I to J and do something skew in the Z direction. But I want one that's going to be just a simple rotation about the Z-axis.
Okay.
I'm going to take out that skewy stuff. The skewy stuff is the part that is corresponding to moving us from one Sylow subgroup to another.
Mm-hmm. Wait, just let me recheck. I don't know, sometimes like when I get lost I forget all the definitions. What is this? If A and B are supposed to be conjugate, doesn't matter if they're in the center or whatever, then it means that the conjugate of A with respect to some element X is equal to the conjugate of B, right?
Yeah, the conjugate of A by X is equal to B, or vice versa.
Right, so here we have A is equal to the conjugate of B. So A and B are conjugate in G, not in the center, right?
Yes.
Okay. Now if I say that if A and B are conjugate in G, then A and B are also going to be conjugate in the normalizer of B.
That's what we're trying to prove.
And I believe, oh wait, is that what we're trying to prove?
Yep.
Okay. Um, Alright, so here's what I think. So so not y. So A is equal to some x b x inverse. A and B are in a Z, and X is in G. Now, we have CG of CG. Wait. CG of A, the centralizer of A. Oh, okay, here's the thing. Alright, so a centralizer of A. Remember, centralizer of A contains stuff from G, such that you always get back G when you conjugate, right? So contains all the small g's such that G inverse is A. Now, if you think about it, as B is in Z. Now, wait, I'm confusing myself. Wait. As A is in the center of P, then the centralizer of A is going to contain P, because again centralizer is filled with the elements that are that you can conjugate with A to get A, and as you are in the center, the only things that fix are, wait.
I'm believing you. The centralizer of A is going to be everything that commutes with A.
Right.
And since A is in the center, it commutes with everything in P.
Right. So if A is in the center of everything that commutes from P, then P is going to be also in the centralizer because it's part of the things that commute with A. Right.
Yes.
Okay. So that's done. CGA is a parent group of Z of B. Now the other claim is that that XPX inverse. Oh right, XPX inverse is the conjugate of P, right? And as Y is equal to as A is equal to XBX inverse, A is equal to XBX inverse. Right, so if you think about the center of the conjugate of P, so center of Z of XPX inverse, what would that be?
Not sure. I know that XPX inverse contains A. I don't know whether A is in the center of XPX inverse anymore.
Right, because see, the center of XPX inverse is going to be all the things that commute with XPX inverse, the conjugate of P. Right. Yeah, now if the conjugate, you're taking commutative elements that of the conjugate of B, then as A is a conjugate of B, A is going to be in this, right? A is going to be in the center of the conjugate of P, isn't it?
I'm checking.
Right, because if you see A times XP.
Yes.
Right?
So I think. I think I might have been asking this before, but does conjugation preserve the center, or is that something that we rejected?
I don't know.
Is the center of P mapped into the center of XPX inverse by conjugation? Is that what you're claiming?
No, I'm saying that this center of XPX inverse is also going to be a subgroup of the centralizer of A. And this is because A is in the center of XPX inverse. So A is included in like all the things that commute with XPX inverse. So A commutes with XPX inverse. Then everything that commutes with XPX inverse is also going to commute with A. Meaning the center of XPX inverse commutes with A, meaning it's in the centralizer. I'm making some rapid implications. Yeah, I mean, this is primarily because you can write A is a conjugate of B, right? And A is a conjugate of B, and it is in it is going to be okay, so I don't know, let's just like take this as like for faith for now. We're going to prove it later. I believe if we prove this, I believe the proof is pretty much done for the problem. So the claim
Okay, so
so
take a
let's
step back and catch me back up again.
sorry?
So take a step back and let me write down what you're saying.
Yeah, so I just said that the centralizer of A includes both the Sylow group P itself and the conjugate of P with respect to X. The conjugate of P with respect to X. Yeah, contains both of those things.
Okay.
Right, and the goal, the analogy is that we proved P is in the centralizer of A because A is in the center of P, right? That was the main argument there. Here,
Sure.
in the other case also, we are trying to prove that the conjugate of P is going to be subgroup of centralizer if the center of the conjugate, Z of XPX inverse, contains A. Right, so that's the analogous argument.
So that's the main thing we'd have to show is that A is in the center of XPX inverse.
Yeah, right.
Or at least that would be sufficient.
Right. So now what you do is you apply Sylow on this centralizer. So Sylow applying on the centralizer means that if you pick something from the centralizer, let's say a Z, if Z is in CGA, then the conjugate that we took, XPX inverse, is actually going to be equal to ZPZ inverse because Sylow P groups, P subgroups, whatever, are all conjugates. You see that?
You're gonna have to say it again.
Yeah, so I just said if you take something from
I'm
this,
accepting on faith.
no, the only thing that
Something from the center.
the only thing we've accepted on faith is that the conjugate of P is in the centralizer. I think I'll try to prove that. But now
Okay.
I'm saying that if you have
Take that for now.
right, if we have something from the centralizer, if we take something Z, then we have it from the centralizer, so right, and then if you take the conjugate with respect to this Z, so we have Z P Z inverse. That is going to be equal to X P X inverse.
Okay, so if Z is in the centralizer of
Yeah.
Z of P,
Z is in the
The
centralizer of A. We're always talking
A.
about centralizer of A. Yeah.
Okay, so if Z is in the centralizer of A, we're going to look at ZP Z inverse. So wait a minute, is this big P? Z big P Z inverse?
Yeah, Z big P Z inverse, yeah.
And what is that going to equal?
To X P X inverse.
Why?
Because because by the virtue of things being Sylow-like, the conjugates are going to be the same of the Sylow P group. I have to use a better argument. Let me look at the theorem again. Right, so because from Sylow theorem, I guess, all groups that are generated by no, this one. There was something about conjugacy.
All the Sylow P subgroups are conjugate.
Right? All these Sylow P subgroups are conjugate, and we are using the fact that XPX inverse is a subgroup, and so is ZP-Z inverse.
If Z was just anything in the centralizer of A?
Right, so if Z is anything in the centralizer,
It seems like that'd be a coincidence for it to equal XPX inverse.
Oh wait. Remember, P is a subgroup of the centralizer. Now, P is the Sylow P subgroup, so it's like the maximal P group, right? Yeah? Give me a second, someone's calling. Okay, so I believe we're close enough, but let me see.
I think I'm getting close to what you're saying. So since the centralizer of A contains both P and XP inverse, and both of those are Sylow subgroups of Z of A. Therefore, they're conjugate within Z of A.
Yes.
That's why there would have to be a Z in Z of A, or C of A.
Mm-hmm.
Centralizer is a Z. There'd have to be a Z in the centralizer of A, so that Z P Z inverse equals XP X inverse.
Right, yeah. The fact that they're in the
Much
centralizer.
like the earlier claim, I'm still buying that because they're both P subgroups of the same group.
Right, so yeah, it relies on the fact that XPX inverse is a subgroup of centralizer. Mm-hmm. I guess, yeah, I mean, as like both of them are in the centralizer, so they commute with A, and they're both,
So if Z
mm-hmm.
is in the normalizer of P, then we're done.
If Z is in the normalizer of P, we're done. Yeah.
Oh, wait, does Z still take B to A?
Z,
Oh, no, it doesn't.
no.
No, Z leaves A alone.
Yeah, Z fixes A, yeah.
So Z's not the element Y we're looking for. Because we're looking for something that takes B to A.
Wait. Okay, I think I got it. So here's the thing. Instead of Z looking for Z, think of XZ inverse to be in the normalizer, right? If XZ inverse,
Say that again, please.
XZ inverse is in the normalizer, right? So if you assume that XZ inverse
Normalizer of P.
P, yeah, normalizer of P, N of P, then XZ inverse
Yes.
P x z inverse of inverse gives you the fact that x z inverse p z x inverse is equal to what is that? Wait, what does that give? If x z inverse is in the normalizer, oh, okay, why were you looking for that?
Oh, you got it. You got it.
X z inverse with b. You conjugate that with b. It's done. See that?
Yes. Yes.
Yeah, you'll get b back.
You end up with Z inverse X, B, X inverse Z. And then the XBX inverse in the middle is the same as A.
Yeah.
And then why does A commute with Z? Because Z is in the centralizer of A.
Yeah.
So you swap those and you get A.
Yep.
I think you got it. You can write it up?
Yeah. Damn, that was good.
Yeah, I think we need to stop while we're ahead. I'm feeling good about that. I think you can put everything together and have it. I think
Yeah.
I'm going to be studying for tomorrow, but it's going to be hard to keep my hands off of this one to see if I could write it up too.
Yeah. Oh.
John, that was a good one.
Mhm.
That was more satisfying than counting groups of order 18.
Yeah, certainly. Ah, damn.
Oh, nice work. That was a long session, but that was
Yeah.
totally worth it.
Indeed. Pristine. It was
And
a
now
good
back to
problem.
modules. Yay.
Yeah, modules. Okay. So tomorrow we have another lecture. I don't know what we're covering even.
I think a lot of it is looking at dimensions. So you more or less create bases for modules,
Right. Okay.
and then look at their dimensions. And then there's stuff about trying to show that that's invariant. When I was skimming it, I noticed that there was several things in the middle where he was saying that the following are only going to be used in a couple of sections of the book.
Mm-hmm.
So it could be that we can skim lightly over part of it.
Okay.
We do get to use Zorn's lemma again. Yay.
That's good.
Now, okay, here on page 185 of Hungerford.
185.
Down near the bottom.
185. Oh. Dimension, invariant dimension, rank. Oh, okay, he's making his way
There
into...
we go. Up just a little. There.
Yeah.
He's saying results 2.9 through 2.12 are not needed in the sequel except for those two sections. And 4.6 is algebra. Sorry, that's modules over at PID.
Right.
So we
Last one
will
is
see
algebra.
that.
Yeah. We're going to see everything.
And that's about a page
Mm-hmm.
having to do with the invariant dimension property.
Of what? Of groups?
The definition's definition 2.8. So something I think that everybody's going to prove is under the right conditions. Well, we know that any two vector spaces that you can define the dimension of a vector space by saying how many elements are in a basis.
Right.
And he's trying to do the same thing for very general rings. So Theorem 2.7 is saying that if you have a vector space over a division ring, then any two bases have the same cardinality. Apparently that's not true for general rings, but they're saying we're going to distinguish a class of rings by saying that for every free module over that ring, two bases are going to have the same cardinality.
Mm-hmm.
And that's a property of the ring. So division rings have that property.
Yeah.
And then he's going to do some proofs about rings that have the invariant dimension property. Then at the bottom of page 186, he goes back and says, okay, now we're just going to talk about vector spaces over division ring.
All right. He made the transition.
And finish this section.
Yeah.
So, other books I'm not finding other books that define vector spaces as being over division rings. I mean, the standard thing is to do it over fields.
Yeah.
So this feels like yet another place where Hungerford is just going more abstract than most other books.
Right. And that's good, actually.
So
Because...
we may be seeing some stuff that's useful, but I'm thinking that chances are we're not going to need to deal with anything more general than vector spaces over fields. Or at least vector fields over PIDs or something.
Okay.
Who knows, but just my gut feeling is that rings that do not have the finite dimension property, what is called? Invariant dimension property, I've already forgotten, I've closed the book, are pathological in some way.
That do not let us have vector space.
Unlikely to run into those critters in the wild, right? Invariant dimension property. So anyway, I'm just saying that so that if we're getting up toward proposition 2.9 and we're running out of time, then we can probably safely skip ahead to theorem 2.13.
Right.
Try to finish it. And then it's going to be doing kind of familiar but important things about dimensions of vector spaces.
Yeah. I'll try to go through them beforehand so that I know I just pick whatever is important.
Well, time's running out, right?
Yeah. So, today was nice. We solved a whole problem from hosting.
Today was wonderful.
Yeah.
That's right. Something that I couldn't solve in a week, we solved in a few hours. That's good.
Okay.
It feels like an accomplishment.
Indeed. I mean, of course, this kind of like discussion is very helpful.
Yeah, I wish that... But I don't know whether anybody else would do it at this point. I think we've missed the chance for this course, but
yeah,
it kind of would be fun if there were like an informal discussion time during the week where, you know, a couple of days after, or maybe like a day or two before the homework's due, so that everybody's had a chance to think about it. Just get together and see if we can hash stuff out and get some ideas to try to knock the rest of the problems out.
Yeah.
Anyway, I think it was a great use of time today.
Yeah.
So
I'll let you know if I decide when the review session is going to happen, because we certainly are going to have that. So yeah.
Yeah, I saw your note. Sounds like some good stuff.
Okay, have a good day. Thanks for your time, and see ya.
You too. Same. See you tomorrow.